This is a chemokinetics podcast in which the rate equations for unimolecular, bimolecular, and even systems of chemical reactions will be discussed and derived. In addition, approximations for simplifying sets of equations will be introduced. From the discussion of bimolecular collision theory, we have the rate equation for a single reaction of species A and species B combining to form products. The rate of production of these products is K times the concentration of A times the concentration of B, where the rate constant K has the temperature dependence of T to the exponent n and the exponent of the activation energy divided by RT. But when combustion mechanisms consist of actually several of these or as many of these reactions, each of which can have a different order. The following discussion looks at dealing with these more complicated cases and how simplifications can be made. Let us look at the rate equations for the unimolecular transformations between species A and species B. For the first case, the non-reversible transformation of A to B, the rate of production is simply minus the rate times its concentration, i.e. the concentration is decreasing. The increase of B is also dependent on how much A there is. A reversible reaction of one product and one reactant is also first order. Though thought as two independent reactions, one in the forward and one in the reverse, we get the expected equations. But now, for example, the molecule A has two sources in sinks. In the forward direction, A is being converted to B at the rate of minus K times the concentration of A, note the negative sign. However, at the same time, it is being created by B converted to A at the rate of minus KB. Thus, the final rate of production of A is the sum of the forward and the reverse reactions. Finding the concentrations of B is exactly the same principle. Just as in the previous case, the total rate of production is the sum of all the sources in sink of the molecular species. For the forward reaction, there is only one source for each rate of production, namely plus or minus K times A times B. The rates of all the species are basically the same, except for the sign, production or destruction of the species. However, for the reversible case, once again, there is the effect of both sides of the reaction. In general, to determine the rate of production of the species, first, collect all the reactions involving that species. Then, add all the rates, with concentrations depending on order, producing the species. Then subtract all the rates that are consuming the species. For the complex mechanism, one has a set of differential equations, one for each species. On the left-hand side, the differential, and on the right-hand side, a polynomial expression in terms of the rates and the concentrations of the species. A more typical case, even for the simple example, like one part of the hydrogen mechanism, the rate of production of just one species can be quite complex. Each species differential is equal to a complex polynomial. So n complex differential equations must be solved to determine the time evolution of the species within a given mechanism. This should give an indication why kinetics is a difficult computational task when dealing with, for example, reactive flows. Sometimes, with simpler systems, there are alternatives to having to solve numerically a complex series of differential equations. These are often the critical assumptions used to estimate fundamental rate constants. Two such common methods are quasi-first order and the steady state assumption. In bimolecular reactions, sometimes one of the reactants, for example B, has a relatively large concentration. The consequence of this is that its total concentration does not change much. This is the pool approximation. This simplifies the second order equation to a quasi-first order equations. For example, suppose that C is 1,000 moles per liter and that B is 1 mole per liter. Even if the reaction A plus B goes to C went to completion, meaning that all B would be used up, C would be still fairly close to 1,000, i.e. with some assumptions, 999 moles per liter. This means that the K concentration of B is relatively constant, and only A is changing significantly. Thus the rate equation can be thought of being basically first order in A. If a molecule is in steady state, then that means that its concentration is not changing. This means that the consumption and depletion rates are the same. It is important to note that the molecule does indeed have a non-zero steady-state concentration. Mathematically, a molecule is in steady state when dA dt is equal to 0. This fact can be very useful in simplifying a set of differential equations in a reactive system. For each molecule in steady state, a differential equation is eliminated and replaced by a purely algebraic equation, which is simpler to solve. A typical two-reaction example is one where a fast reaction is followed by a slow reaction. This one is taken from the NOx mechanism. Here we assume that N has reached an equilibrium state within these two reactions. Setting dN dt equal to 0 leaves an algebraic equation where N can be solved for. The computations show that first the steady state concentration of N is non-zero and dependent on O, N2, and O2. Consider the reversible bimolecular reaction involving the reactants A and B and the products C and D. Under equilibrium conditions, the rate of production of the reactants is the same as the rate of production of the products. Setting the differentials equal, we get an expression relating the forward and reverse rate constants and concentrations of the reactants and products. Collecting the rate terms on one side and the concentrations on the other side, we have an expression for the defined quantity, the equilibrium constant. The equilibrium constant gives a ratio of the reactant concentrations to the product concentrations. For example, a large equilibrium constant means that the reaction goes close to completion and a significant portion of the species went to products. By definition, the Gibbs free energy is G equals H minus Ts. In thermodynamic definitions, the term H minus Th occurs so frequently that it's justified to define a new variable. The Gibbs free energy is the thermodynamic quantity that represents the useful work from an isothermic isobaric system. Gibbs defined it as the greatest amount of mechanical work, which can be obtained from a given quantity of a certain substance in an initial state, without increasing its total volume or allowing heat to pass to or from external bodies, except such as close of the processes are left in their initial condition. The connection between thermodynamics and kinetics can be found with the Gibbs free energy. In this lecture, this will be taken as a definition. The relationship holds for ideal gases. Note that this is equilibrium with respect to partial pressures. The relationship between equilibrium defined with concentrations has some extra constants and is dependent on the number of reactants and products. The significance of its use will be able to relate the equilibrium constants, even the forward and reverse rates, to thermodynamic quantities of entropy and enthalpy. For example, in numeric programs, solving for kinetic systems, if the thermodynamics of a reaction is known, i.e. the enthalpy and entropy, and if the forward rate is known, then the reverse reaction can be derived. From the two expressions for the Gibbs free energy, we can derive what conditions favor completion to products. Solving for K in terms of the Gibbs free energy, we get an exponential. Then, substituting for G and separating the two exponentials, one for enthalpy and one for entropy, we get the following expression. If the equilibrium constant is greater than 0, meaning then the reaction favors the products, the forward rate is greater than the reverse rate. An exponential is greater than 1 if the term in the exponential is also greater than 0. So the first term says that if the change in enthalpy is less than 0, meaning the reaction is exothermic, then products are favored. The second term says that if the change in entropy is greater than 0, meaning there's more molecular chaos, then the products will also be favored. Note that this is not a proof, but rather an example why the Gibbs free energy was defined in the first place.